Hello. In this video, we will briefly explore some basic tools and resources at the foundational level of AutoTherm's pyramid. They function as basic solvers that higher level applications utilize to perform essential tasks. These tasks include automatic unit conversions, assigning material properties, and conducting background mathematical operations. However, they may also be used independently, enabling users to access these functionalities directly. Additionally, these topics have a broader range of applications, which is why they are positioned at the base of the pyramid, making them highly beneficial for students and professionals in engineering, science, and mathematics. The first of these basic tools is units and dimensions. AutoTherm's units and dimensions toolsets enable quick conversions, allowing users to work seamlessly with various measurement systems relevant to their engineering tasks. Units and dimensions are accessed from the top menu at the very left. The first menu item is its resources, which is written text with some definitions. And as you go down, you'll see the primary units in SI, English, and US customary system. To convert units, select an engineering dimension from the available list. Let's say we want to convert volume. Input a value in any unit, and you will instantly see its equivalent in other units. For instance, if we enter 15 milliliters, you can instantly see the equivalence to 15 milliliters in all other units. For example, it's approximately 1 tablespoon or 3 teaspoons. Sometimes equivalent values are presented in different but closely related units of measurement. A good example of that is in heat transfer coefficient slash thermal contact resistance. Let's say we have a thermal paste with the interfacial contact resistance value of 0.75 K inches square per watt, which is a common unit for these things. As you enter the value, you notice this is equivalent to heat transfer coefficient of 2067 watts per meter square K, or H of 2067 watts per meter square K. Now, this is what's frequently used in thermal and CFD software packages to model thermal contact coefficients. The next basic item is the constants and parameters menu pick. This menu offers quick access to frequently used constants, numbers, and non-dimensional parameters. There are no automated tools in this category. The general constant category lists key engineering constants. Here we have their names, values, and comments and definitions. For example, pi has a value of 3.14159, goes on forever, is an irrational number which is defined as the ratio of a circle's circumference to its diameter. As you can see here, we have all of the engineering constants that we frequently use, such as gas constant, Stefan-Boltzmann constant, among others. Next, the order of magnitude option provides an interesting range of heights, depths, distances, and temperatures, from very small to very large for some well-known physical objects and locations. The section on non-dimensional numbers and parameters present dimensionless parameters commonly used in heat transfer and fluid mechanics. While this overview serves as a reference, these parameters are discussed in greater detail throughout various chapters on heat transfer and fluid mechanics topics. As we can see, these are presented first by their name and how they're defined, their significance, and the area of application. As you can see, the first group is what we call numbers, a familiar number like Prandtl number, Nusselt number, Reynolds number, and so on. And then we move into uh, ratios and coefficients and factors like friction factor, skin friction factor, and things like that. As an example, if you look at Grashof number, you can see how it's defined, and it's a ratio of buoyancy forces to viscous forces, and the area of application is in natural convection. Next, we have the very important topic of mathematics for engineers. Mathematics is the fundamental language of engineering and serves as the primary tool for designing, analyzing, and optimizing physical systems and technologies. It enables engineers to predict behavior, ensure safety, calculate forces, and solve complex problems using algebra, calculus, differential equations, and linear algebra. Math resources provide you with instant access to commonly used definitions and formulas. For instance, let's take a look at the algebra resources. Other topics have a similar structure. Selecting algebra from Math's top menu offers a number of sections that we can quickly jump to. But let's start at the very top. Here we have a text panel again that walks us through various topics in algebra and pre-calculus. At the very top, we have discussions on background and overview, and then we get into branches of algebra. There's a short discussion on variables, expressions, and equations. And then we get into functions, which are the foundation of algebra and calculus. There are some general discussions at the top, and there are some key aspects of plotting that applies to all different types of functions. And then we get into common function types, starting with linear function, and we get into quadratic function. Again, general discussions, some definitions, some formulas, and for each one of these functions, we have a section that shows graph behavior for different types of functions. So here are different types of graphs that we can encounter for quadratic functions of various types. Then we get into polynomial functions. Again, the discussion at the top, some general definitions about n behavior and multiplicity, which tells us what this thing is going to look like, what's the behavior of the function. And then we get into different graphs that shows behavior of very different polynomials. The next one, similarly, is the rational functions. Same as before. What are holes? What are the vertices? What are the asymptotes? And so on. And again, graph types. Exponential functions, growth and decay, general definitions, and graph types. And then there is a section on exponent formulas that everyone should know. Then we get into logarithmic functions, some definitions at the top, a lot of examples, and again, we get into graph behavior for various types of functions. And again, we have a listing of logarithmic formulas. Next, we get into a different section. It has to do with factorization and expansions of algebraic expressions. At the very top of that, we have the identities that here we have all of them at our fingertips. And one of the important topics is how do you factorize a quadratic equation that we encounter a lot in engineering. And here we have discussed different methods. There are foolproof methods for factorizing quadratic equations when the leading coefficient is 1 and when the leading coefficient is not equal to 1, with a lot of examples showing how you do that step by step. Now, one of the important things that you need to do when you factorize these things is to have access to factors of numbers. And because of that, here is provided a table that lists factors and prime factors for all numbers between 1 and 100. Let me go through a couple of them to show you how it works. So let's say 12. So here we have 12. The factors of 12 is either 1 times 12, 2 times 6, 3 times 4. Now, if you have odd number of these things, for example, 4, so the factor would be 1 times 4, and the middle one times itself, 2 times 2. All right, then we have the prime factors, and the last column shows which one of these numbers are prime numbers. Again, the table goes all the way down to 100. So this is a type of the resources of one of the math topics. Other ones are very similar. So you can be in geometry, trigonometry, calculus. Math tools are organized at the bottom of the math menu, which differs from the thermofluid tools that are placed in their respective chapters. Here we can see a number of options, some simple tools. Let's take a look at a couple of them to see how they work. For example, if you click 3D shapes, as expected, we can see a form with the number of options presented here. Let's say we have a hollow cylinder with an inner radius of 1 inch, outer radius of 2 inches, and a height of 1, let's say, foot. And you click update, and it will show you volume and various surface areas. If you wanted to see, for example, the base surface areas in inches square, you just change the unit to inches square. And we'll show you that. So it's a productivity tool. Very simple. Just save some time. Another thing that we do often is solve system of linear equations. So again, we go to Math Tools, System of Linear Equations. And here we have an environment where we can set up our system. The A matrix goes over here. That's the coefficients matrix. Constants go in the B vector, and the results will be displayed in the X vector. The first thing we need to decide is how many equations we have. Let's say, for example, we have 9 equations, and you click initialize, and you can see your system is set up for 9 equations and 9 unknowns. If you have a lot of equations, you can read from a file. You can have hundreds or thousands of equations this way. Let's solve an example to see how this works. And I came across this example online. I thought it was interesting because the results are 1, 2, 3, 4, 5. And let's set up our system to see if we can solve this thing. All right. First of all, this is 5 equations, 5 unknown. I have to change that to 5. And the first row is pretty easy. 1, 1, 1, 1, 1. The second row is 0, 2, 1. 0, 2, 1, minus 1, 1. Third row is 2, 0, 3, 0, 1. 2, 0, 3, 0, 1. The fourth row is negative 1, 1, 0, 2, 0. And last row is 1, 0, 0, 1, 3. Okay, and the uh, constants are 15, 8, 16, 9, 20. 15, 8, 16, 9, and 20. And hopefully we entered everything correctly, and you click on solve. You get 1, 2, 3, 4, 5 for the solution, which is the expected solution from the system. So here we can see we can easily set up a system to solve a system of equations, which we frequently run into in engineering. The last group of basic tools involve material properties. Here we can see we have a number of options available. The very first one is solid properties. Clicking on that opens an environment displaying thermophysical properties of various solids. You can see properties are separated by columns, and the very first column we have the solid material name. Then we have density, specific heat, thermal conductivity, electrical resistivity, and temperature coefficient. On the left side, there are ways to reduce these using filters. For example, if you click on one of these, for example, metals, it only shows materials in the library with electrical resistivity and temperature coefficient in the range of metals. Another thing you could do is you can search by name. For example, if you put copper here and click search, it will show you everything with the word copper and the material name. Another way to look for material is through a range of its properties. For example, if you go to thermal conductivity, let's say we're looking for something between 150 and 300 watts per meter K, and you search, and it will give you all the material in that range, as we can see. Next, we have fluid properties. It's presented the same way. We have properties separated by columns. The first column here, those temperature in Kelvin. Then we have density, specific heat with constant pressure, thermal conductivity, dynamic viscosity, kinematic viscosity, thermal diffusivity, and the Prandtl number. And here on the left, we can see what fluid it is. The default fluid is air. If you want to change the fluid, you go and pick something else, for example, water. And the properties are displayed the same way. The next three menu items involve thermodynamic properties, saturated properties, superheated properties, and ideal gases. Now, these same tools are available also in thermodynamics, properties of substances, and you can see they're located in their proper location. Let's first take a look at the saturated tables. If I click on that, the form will open up, and you can notice there are two panels. The top panel is the saturated table line corresponding to temperature and pressure. And the bottom panel is when you want to find a property, either knowing the quality or one of the other properties. So let's take a look at an example. I think the easiest way is to go to a thermodynamic property table. Here's for water, for saturated water. So I'm going to go back to our tool and let's place it on a line that we are interested. Let's say we want to look at the properties at 120 degrees C. So if I enter 120 and update, you can see all the properties on this line displayed. Uh, Pressure is 198.67 and everything else matches up. So let's take a look at, for example, enthalpy of the saturated vapor, 2706, and it's right here, the same thing. Okay, now if you have something that's not on in here, like 122.5, there's no problem. It will just interpolate and you get the correct values for that. Now let's take a look at the bottom panel. If we know the quality, for example, if the quality is 75% or 0.75, you say update, you get all the properties interpolated between saturated liquid and saturated vapor with the quality of 0.75. Alternatively, if you know a property, let's say enthalpy is 1925, and you update, it will calculate your quality and other properties similarly. Okay, so now let's take a look at the superheated properties. Similarly, if you click on that, you have the superheated properties. We'll go back to our property tables and the superheated section, and let's examine the pressure block at 0.6. You can take any pressure block that you want, obviously. So if I go over here and let's compare at 0.6 at temperature 300. So I enter 0.6 MPa and 300 degrees C, and you can see the properties are shown exactly of what they are. Of course, the usefulness of this tool comes when you can't find it on the table. Let's say you are at pressure of zero point 0.7 megapascal and temperature of 325. Okay, so neither one of these things are there. So zero point 0.7 is between two pressure blocks, and 325 is between two temperature lines. If I say apply or update, you can see the values immediately. But if you wanted to do it yourself, you have to do a number of interpolation between pressure blocks and temperature blocks, and it would be a tedious process. So it saves a lot of time. Now let's go back to our main page. The last menu item has to do with ideal gases. This also is available from thermodynamics chapters, just like superheated uh, tools. So you click on ideal gases, it opens the ideal gas form. The portion on top gives you molar mass, gas constant, and critical point properties for gases. Default is air. You can go to uh, any material and will give you these values quickly. Uh, this portion on the left is you can enter properties and it gives you the ideal gas, uses ideal gas equation to give you other properties. Let's say if you have temperature of 300 and pressure of 150 kilopascal, and it gives you the density, specific volume, and specific heats, and the ratio of the specific heats. Now, the right side, it gives you, uses the ideal gas laws, but it gives you the endpoint of a process. So you could actually fix a state, which basically is enter properties, or you can use a process. Let's say you're going on an isentropic process to, um, let's say you go into a higher pressure of 200 kPa, and this will use an isentropic process starting from this point to get that. Of course, isentropic process means S2 minus S1 is 0. So you go through and then you actually calculate U2 minus U1, H2 minus H1 using the variable specific heats at these points locations. I hope this video has helped you become familiar with AutoTherm's basic tools and resources. Thank you for watching, and I look forward to seeing you in the next video.